Hi everyone, this is late at night here, but we'll be continuing the series building GPT from scratch, and this is part 2. So let me tell you what we'll be doing in this video. So the goal is very simple, that we'll train a neural bigram model. Now if you remember from the last video, we established the idea of embedding, where we convert words into numbers and not just a single integer but a series of numbers, so that each number adds more and more information. And we also looked at a very simple model, which was a bigram model. The model would be similar to that. Right now, we'll still look at the last word of the sentence and we'll predict what is more likely to come next. That is the idea, but right now we'll not be doing the counting model, but a neural network model. Well, we write a very small neural network, and the machine or the model will learn the pattern on its own, and then we'll make the prediction and we'll see how far can we go, right? So that is the short context of this video, and what we'll be building. We'll be going through the code, and I'll be showing you some great visualizations of tensors and neural networks. So it's going to be a fun session, and with that, let's get started. So the first thing that we have to do is to build our training data, the data we'll use to train our model. Now for the text model or for the language model, it's very simple for us. How? I'll show you quickly. So quickly look at the code here. By the way, we'll be using PyTorch, which would make our job easier. So if you remember from the last video, we have a vocabulary of 500 words, and using those same 500 words with different combination and different sentences, we have the huge text of roughly around 160,000 words in total. So that's our overall data. But the data we want for training is, we need the input and the target values. So if you were to look at this line 56, here out of all the data, I'm basically taking everything as an input, simple. But what becomes a target is simple. We have just shifted the input data by one word. So for example, let's say the input was, this channel is debug explains. The target becomes just shifted by one word, channel is debug explains, full stop, right? So for the input, we are not taking the last word. And actually this is the reason why these large language models could be trained on the whole internet data, because it was literally this easy. Get the input shifted by one word and you have input and the target values. So for the target for the word this is the word channel, because channel is supposed to be coming next to word this, okay? But when I was telling, so when it comes to the training on the image data, it becomes difficult because you have to literally label each image. Okay, this is a cat image, this is a dog one, and so on. But for the text or the language data, it's much simpler. And now let's move on. Okay, before that, have a look here. What is this? This is word to ID and ID to word. So in the last video also, I told you that we'll map each word in our vocabulary with an integer. So full stop gets mapped with 0, and the last word, so it's in the alphabetical order, gets mapped with 499, because our vocab size is 500. So you can see in the terminal as well, this is our training example. The two overall words are 163,000, and we have the input and the target values as well. Now let's come to the model that we'll be using, or the neural network that we'll be building. So our neural network will have only 2 layers. So that's all. We'll keep it very simple, and the dimension of our model is going to be 32. I hope you remember what is the dimension. It is simply how many numbers you're using to represent each word. So 32. Now what are we doing here? So this is the neural bigram class, and in that, look at this line, nn.embedding, we have vocab size times the dimension of our model. So this is basically, imagine this as a huge table, which is the dimensions are 500 cross 32. So for each word, which is each row of our table, we'll have 32 numbers, simple as that. And right now, this is going to be random numbers. Right now, our model does not know anything, and it does not understand any word or does not have any context to it. But after the training, the similar words will point out in the same direction, and we'll see that happening at the end of the video. So this is a look. So this is a huge table of 500 cross 32, and this is a linear layer that we have built here. So I'll help you visualize it. Look at the dimensions here. So it basically means D model. So we'll have in our input, we'll have 32 numbers and the output layer will have 500 numbers. So let me help you visualize it. So first of all, let's imagine the embedding table, which is 500 cross 32. And here's how it looks like, right? So each row represents each word, and each word is represented using these 32 numbers, and right now they are absolutely random. And then we'll take these 32 numbers and we'll put that into a neural network, and this is our neural network. And I have not shown you all the 32 neurons because it would be messy. So imagine instead of 3 we have 32 neurons in our input layers, and instead of these 5 we'll have 500 neurons in our output layer. So you get the idea now. So we'll take out each word here, and each word will give us 32 numbers. We'll take those 32 numbers and put this in our neural network. Those 32 numbers act as the input here, and it will give us the output as 500 words. Now why the output is 500? Basically we are asking each word, tell me which word out of the 500 words in our vocabulary, which word is most likely to come, and it will assign certain number to all those 500 numbers. The higher the number, the more likely it is to come next. That's the basic idea. And in between, if you remember, I've already made a video about neural networks. I've explained them from the beginning, from the scratch to absolute beginners. So please do check it out if you're not familiar to this architecture. Well, these are called the weights of our neural networks, and we also have the biases as well. So now let me tell you what will be the total parameters of our overall model right now, whatever I've shown you till now. So the first thing is this embedding table. So overall, if we multiply 500 times 32, that's 16,000 numbers. So these 16,000 numbers are our parameters. We'll have to nudge these values to make our model better and better. And also, looking at this neural net, imagine this as 32 times 500, which is again 16,000. So 16 plus 16, total 32,000 parameters, plus we'll also have biases, right? So in total, we'll have 500 biases here. So overall parameters becomes 32,500, right? So these many numbers will be nudged as part of our training to make sure our model predicts better words. That's the whole idea. I hope you're getting it. I've also printed it, and I think my calculations are correct. Okay, you can see right here. So overall parameters are 32,500. Okay, so now let's move on. And also in this video, I want you to get familiar with more terms and terminologies like logits, softmax, and cross-entropy loss, gradient, and optimizer, and all of that. So I'll help you do that as well. So just now I explained you that these 32 numbers will give us the output as 500 numbers. Now these 500 numbers are nothing but logits. So read here, logits are unbounded opinions. Big means likely, negative means unlikely. But they don't add up to anything meaningful. So we'll use a function called softmax, which fixes this, and it will do two things. So I explained it in my earlier videos. First of all, we have to make every term positive. So we'll do this. We'll raise each term to the power of e so that everything is positive, and we'll divide each term by the total sum. So divide by the total, so everything adds up to 100. And basically, softmax function gives us the final probabilities. I'll also show you on the table as well. So as you can see right here, let's say these are my logits, total 500 numbers. And when I'll apply softmax, it turns into probabilities. Right now you're seeing all the zeros, not all the zero basically, because these are negative terms, so they are roughly 0 here. Let me take let's say we have only 10 numbers, okay. So these are the logits, and then this becomes our probability. So you get the idea. We make every term positive and divide by the total. That basically, it makes sure that everything adds up to 1. And that means this gives us the probability of each particular word, right? Now, how do we know that which word is number 9, right? We have mapped each word with an integer. So full stop is mapped with 0 and the last word is mapped with 499. So we'll have to go back to that particular mapping and get the word which is placed at number 9. Perfect. So right now, what do we have? We have the probabilities assigned to each of the 500 words. And now we'll calculate the loss, because certainly at the starting our model's guess would be wrong. So we have to tell our model, hey, how wrong you are. And then we'll go back into our network and we'll change the parameters. You remember those 32,500 words, or sorry, numbers. We'll change those so that next time our model guess is better, right? So now we have to calculate what's the loss and how wrong we are. And it is going to be very simple. Just read this line. So loss would be negative of log and probability the model assigned to the true next word. So we know the target values. We already built our training examples. So I'll ask what probability you assigned to the correct word. I'll take that value, put that into log function and take the negative. Now, why are we doing this? I'll make it clear right now. So imagine our model gave 100% probability to the correct word. That means our loss is 0 and perfect. It assigned 50% to that word, put that value here and we get 0.69. So as the assigned values goes down and down, our loss increases. So that's what exactly we wanted, and that's why we used negative number and we put log outside it. And again, if the model assigns 0 probability to, I mean, it's completely sure that word won't come next. So we have to punish the model for that. So the loss shoots up to infinity and it is catastrophic. So we have to really change values here. A model, you're going in the wrong direction, like that. And this loss is called the cross-entropy loss. Okay, one more important thing, I've written it down here. We have to do a sanity check. Why? Because in the starting, since everything is random, so what I expect is, I expect the model to assign equal probabilities to all the 500 words. So I'll quickly check whether the loss is going to be this value, negative of log 1 over 500. So by doing this, we can make sure that all the steps are done correctly till here, and then we can move on. So now time for our final step, which is the training loop. And basically we are repeating this multiple steps over and over again. What are we doing? So first we'll fetch the logits and we'll convert those logits into probabilities by using the softmax function. And then we'll calculate the cross entropy loss. And then after we have calculated the loss, we'll go back into a network and we'll nudge our parameters in a way that it reduces our loss. And this process is called gradient descent. I've already covered this in my previous video of neural network. Please do check it out. So this line right here. So right now we need not write those differentiation functions because the PyTorch library would help us do that. So loss.backward, we are going backward into our network, calculating the relation between loss and each of the parameters, and the optimizer.step where we are actually nudging those parameters. And there's one more variable which is called the learning step, which is required in the optimizer step, where we are telling what should be the learning size, what should be the learning step. Should we take big steps of learning or small? So that is also a crucial parameters, and you can see I've defined my learning rate here. So let's begin the training part now. One thing you can see here, we have a batch size and steps here. So what do we mean by batch size here? So we'll send the data in batches. So each batch will have 512 words. I told you each batch will have 512 words and each word has 32 numbers. So the dimensions become this. So the overall dimensions become batch size times d underscore model. So I hope you get this. So this is a batch size, and steps. Steps is nothing but epochs. Many of you would be familiar with this words. So how many times I'll repeat the training loop? That is 3000 for our case. So yeah, let's start the training process. So first step in steps plus 1, basically 3000 times. So first we are picking up random batches of 512 words, and that becomes our input and output target values. Now again we'll calculate the logits. So this is a model. We'll send in the input, and again it will give me logits, which is 500 words. And I'll take those 500 words and I'll calculate the loss. Look here, in the cross entropy, we are sending in the logits and the target values as well. And that becomes a loss. Once we have the loss, we'll set the gradients as 0. And then we'll go back. So we'll find the relation between parameters and the loss function. And then we'll take the step, or will we nudge the values of our parameters. And we'll do this process for 3000 times. And let's see. So I ran it for 3000 times and you can see the loss. We started with 6.4 and we ended with 4.04. Okay, so this is the progress we made. And now let me compare it with the counting model from the last video. So let's say we have the word cat, and we'll see what does cat predicts. So by the counting model, 48% of time it predicts full stop, and by our learning model, 46% time it still says full stop, and you have the complete data here. So you see, like, these are two completely different methods, and the answer is almost same. You can see here why we have not improved much, and I'll tell you the reason at the end of the video. But one bonus thing I want to tell you right now. I told you that those embedding vectors are random at the starting, and by the whole training, after the whole training, those embeddings would be learned. So what would happen is similar words would point in the same direction, and I have the data here. Look. So let's say the nearest words to the vector of cat. Now cat is a noun. So you look here. What do we have here? Hammer, squirrel, leaf, hue, brush. So all nouns are pointing in one direction, or they are in a cluster together. And look at here, chased, which is a verb, and look, sorted, sold, described, which are also verbs. And then we have a determinant, which is, and again we have a cluster of determinants and a cluster of adverbs. So this is literally magic. We started with random numbers with no context, no meaning. We ran this whole process, basically a feedback loop. You make a random guess, we'll tell you how wrong you are, and go back and change the values, and keep doing it thousands of times. And now we have learned something very important, and you can see the result is right in front of you. You can see the embeddings vectors have formed clusters, similar words point in the same direction, and this is literally magic, and this is the beauty of neural networks and AI. Okay, so let's do a quick grammar check. So I did a generation from this same model, and this is the generated text. So some sunny stream wade some distant singer. So again, kind of makes no sense. The grammar is still at 22%. Now you might be wondering, why are we still stuck here? The loss is still 4.04 and the grammar is 22, still bad. And the reason is simple, that we are still looking at the last word to predict the next value. We don't have the context of the full sentence. So the next steps to improve this model is to start looking back in our sentence, and that would introduce us to the concept of attention. So I'm excited for that, and I'll see you in the next video. Thank you very much.